In TR-05, we showed that all the way around the circle is 2 pi radians, meaning the full rotation angle is 2 pi radians. So halfway around must be pi radians. Half of that is pi over 2 radians, and the right angle the same as a 90-degree angle. When expressing radians as a fraction using pi, we include pi in the numerator, so we say and write pi over 2 radians, not 1/2 pi radians. Just put pi right in the numerator. If it's clear from context that a number that includes pi is an angle measurement, we don't have to explicitly include the radians label, because we assume that any angle measurement that includes the pi symbol is measured in radians. If for some reason you have radians expressed in decimals, then you must use the RAD label for clarity, so it won't be mistaken for degrees. Of course, it's never wrong to use the RAD label for radians, even if the numerator includes pi. Okay, back to our angles. This point that we know is 30 degrees is 1/3 of a right angle. In radians, this is 1/3 of pi over 2, which is pi over 6 radians. Knowing that 30 degrees is pi over 6 radians makes it easy to list all the other multiples of pi over 6. Just count around the circle in the positive direction, remembering to skip over the quadrantal bisecting 45-degree angles, since they aren't multiples of 30 degrees. Each step around the circle represents another increment of pi over 6. Remember how simple this looks because when we reduce the fractions, things look so much more complicated for some reason. Angles down in quadrant 3 and 4 will be improper fractions when expressed as radians with pi, since they're all greater than 1 pi radian. Improper fractions are okay when expressing angles in radians with pi. To identify one of these angles, just figure out how many pi over 6 it is. You can use the quadrantal angles as landmarks again, 0, 3, 6, 9, or 12 pi over 6. Then add or subtract. For example, this point represents 3 pi over 6 minus 1 pi over 6, so 2 pi over 6, which reduces to pi over 3 radians. What's this point's angle in radians? 6/6 plus 1/6 equals 7/6 pi radians, which cannot be reduced. One more, what's this angle? 9/6 plus 1/6 equals 10/6 pi radians, which reduces to 5 pi over 3 radians. It's easy with practice. Now let's look at the pi over 4 angles. This angle is half of a right angle. Half of pi over 2 radians is pi over 4 radians. Using this angle as our increment, we can count all the way around the circle again. When we reduce these fractions, we notice that only the quadrantal angles can be reduced, and as we should expect, they match the fractions we already know. The quadrant bisecting angles are pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4 radians. They can't be reduced. Here are all the common angles expressed as radians. You need to know these. I'm not saying you need to memorize these fractions, but you should be able to figure them out quickly. And remember, each of these radian values represents the number of radii that the angle subtends. So this angle could be called 0.7853982 radians, but it's so much easier and more precise to just say pi over 4. That's where the pi comes from. We should know these common angles in both degrees and radians and be able to convert back and forth. If you're given a point, you should know the corresponding measure in degrees and radians, or at least be able to figure it out in a few seconds. If given a common angle measurement in degrees or radians, you should be able to picture the circle in your head and say the corresponding equivalent measure. It's easy with practice. If an angle to convert isn't one of the 17 common angles, you'll need to use a conversion equation. We'll multiply a measure by a conversion factor, which is a fraction that evaluates to 1. The numerator and denominator represent the same measure expressed in different units. When we arrange the fraction properly, the old units will cancel when multiplied, leaving the desired units. Since a full rotation angle is 360 degrees, and also 2 pi radians, we could use these in the conversion factor, But these fractions can be reduced to 180 degrees over pi radians. These are the conversion factors used to convert between radians and degrees. For conversion problems, it helps to label radians explicitly so we can keep our cancellation straight. Let's convert 1.5 radians to degrees. Here's an example of a radian measure not expressed in terms of pi. So we make sure and use RAD to denote the units. Arrange the conversion factor so the unit of measure you want to end up with is in the numerator on top, and the units you're given that you want to convert away from are in the denominator on the bottom, so it cancels out. So we multiply 180 degrees over pi radians, and the result is 85.9 degrees. Remember that pi is a number, not just a symbol. To convert 112.4 degrees to radians, we multiply by pi radians over 180 degrees and get 1.96 radians. These are easy problems. You know you have the right conversion factor when the units cancel. We should now update a few definitions. Right angles are 90 degrees or pi over 2 radians. Complementary angles add up to 90 degrees or pi over 2 radians. Supplementary angles add up to 180 degrees or pi radians. Any definition or reference to 90 degrees or 180 degrees also applies to pi over 2 radians or pi radians, respectively. Please know this circle and be able to say each angle measurement in both radians and degrees. Again, it's easy with practice. The next video is TR-07, a geometry review of triangles.